Volumes of revolution, the method of cylindrical shells. Objectives. By the end of this lesson, you should be able to recognize when the use of the shell method is more practical compared to the use of the disk or washer method. Set up an integral used to find the volume of a three-dimensional region using the shell method. Let's try to imagine rotating this shaded region about the line x equals -1. Will the traditional washer method work? So here's a function, this black graph here, and here's the shaded region that I'm trying to rotate. And I'm trying to rotate it around this line here, x equals -1. So we know that with the methods we currently have, we would be attempting to use the washer method because the region itself is not completely up against the axis of rotation. And if I think about trying to create a washer, well, my cross sections are going to be horizontal. And so if I try to create one of these washers, this is going to be my inside ring to the washer, and then this is going to be my outside ring to the washer. So you might be thinking, well, okay, at this point it seems like I can use the washer method. But when I attempt to find right minus left here, I'm going to run into a bit of an issue because this black graph is all one function. So I need to be able to split it up somehow into thinking about it as the right half of this function here and then the left half of this function here, so I have a right minus left situation. And there's not going to be any way that we can split up a function, so this is some function in terms of x and we would need it to be in terms of y, and there's not going to be a way we can rewrite this function to split it up like that. And in some cases we might be able to, but it's just going to be a lot of work. So that is not the method that we're going to be using. The traditional washer method doesn't really lend itself to this particular problem. Alright, so the bottom line is that the washer method will not work for that previous example. And now to show the explicit function, that was the function y equals 3x minus x squared. And there's no way that we can write this so that it's a function of y so that we can use the washer method. So the actual 3D solid is going to look like the one over here. And what we're going to need to do is use the shell method. So the bottom line is that instead of disks or washers, we are going to create cross sections that are cylindrical shells. So here's an example of a shell. So you can see that it looks like a cylinder, and this particular cylinder has a thickness, and we're going to call that thickness delta R. So of course the cylinder also has a height, and because it's a cylinder with a cylinder carved out of it, this example has a big radius and a small radius. But our goal is we want to make the thickness of each shell, this delta R here, we want to make this thickness go to 0. So we want to make them paper thin, just really, really, really thin. We want this to go to 0, to approach 0. And then we want to add all of the shell's area together. And if we do this, we're going to have the exact volume of the solid. So imagine there's not going to be any thickness anymore to this shell, so it's going to be just a paper thin type of cylinder, and those paper thin type of cylinders are going to be stacked against each other over and over and over again, so wrapping around each other. And if we add up all of the shell's area, we're technically setting up an integral, and that integral will give us the volume. So let's go ahead and take a look at some images to visualize this a little better. Alright, so here are some student-made 3D examples to try to help visualize that this would be the solid object. So here are my solids, and then using different colors, the students try to make these very, very thin cylinders that are wrapped around each other of different heights. So this is an example of the 3D solid, and how we're going to find the volume is we're going to add up each of the cross sections now being cylinders, and since they have a thin approaching 0 width, they're going to themselves have an area that we can explore. And so here's sort of a technical example that the book will demonstrate, is that what we can think about doing is taking a particular width and wrapping it around the axis of rotation so that we are creating these shells about the axis of rotation that we're going to make thinner and thinner and thinner. So here's one example of using, it looks like 1, 2, 3, 4, 5 shells, which of course isn't the exact volume of the solid, but as we continue to make the width of each of those shells thinner and thinner, we're getting a better and better approximation of what the actual volume will be. So of course if we make that width, the thickness of the shell, go to 0, we will find the exact volume of the three-dimensional object. Before we take a look at the formal formula, I want to think about where it comes from. So let's think about just one shell. So one shell is going to be like this cylinder here. So I've tried to draw it to indicate that it doesn't have any thickness to it. It's just this solitary outline that's happening here. And since this thickness goes to 0, imagine a shell as a cylinder with no top or bottom. So there's no top portion here and there's no bottom portion here. It's like a can where the lid and the bottom have been removed. So we can think about the surface area of this cylinder would be the cross-sectional area. And we're trying to add up all of the areas of the cross-section to find the total volume. So let's try to think about what's the surface area of a cylinder with no top or bottom in terms of its radius. So let's start marking this thing up now. So this thing has a height h and it has a radius r. And again, it has no top and it has no bottom. And what I'm interested in is the surface area. So if I were to slice this open down the side length here and unravel it, well, what's it going to look like? It's going to look like just a rectangle. And that rectangle's area is equivalent to the surface area of one of the cylinders. And that's what we're going to want to add up, is all of those surface areas, because the surface area is the cross-sectional area. So if I cut this open and open it up and spread it out, the base of the rectangle is going to come from the circumference of the circle. So the base here is a circle with radius r, and the circumference in terms of the radius is 2 pi r. So this rectangle has a base of 2 pi r. So again, that came from unraveling this cylinder. And then the height is still h. So in other words, the surface area of this can without a top or a bottom, this cylinder, is 2 pi r h, because it's base times height. So the surface area that we're going to need, 2 pi r h, depends on the radius and the height. So that's what we're going to need to write in terms of our function that we're given. We're going to need to express the radius and the height in terms of the function that we're given, that we're going to be rotating around that axis. Alright, on to the formal formula. So we want the volume of a solid of revolution using cylindrical shells, and what we're doing is we're rotating about a vertical line first. So if f of x is continuous and defined on a to b, then the volume obtained by rotating the region about a vertical line, well, the volume formula is still just the integral from a to b of the cross-section, the area of the cross-section. And we just took the time to break down the area of the cross-section. The area of the cross-section was just 2 pi and then the radius times the height. But the radius is going to need to be a function of x, and the height is going to need to be a function of x. Well, 2 pi is a constant. It can be pulled to the front. So ultimately, we're looking for r of x, that's the shell radius, and h of x, that's the shell's height. So what this is going to amount to is the shell radius is going to be found by doing right minus left, and the shell height is going to be found by doing top minus bottom. Before we start examples, let's go over the steps for using the shell method. So we want to draw one shell at any x in the interval, and then we want to sketch the radius from the axis of rotation to that x value that we've chosen that's in the interval of the region. And we're going to write the radius as right minus left. And this portion must include the variable x. So we want the radius in terms of x. And then we're going to find the height of the shell by doing top minus bottom. So the top function minus the bottom function. Alright, let's take a look at some examples. So we want to use the shell method to find the volume of the solid obtained by rotating the area under this function 1 minus 2x plus 3x squared minus 2x cubed about the y-axis. So first of all, let's notice that I'm given a function of x, and the graph has been given to me. So this blue function is a function of x. It's this cubic here. And I want to rotate about the y-axis. So my axis of rotation is right here. And let's talk for a quick second about how we would determine we would need the shell method for this particular problem. So right now you might be thinking, well, the entire region borders the axis of rotation, which is true. So you might be thinking, well, this is a clear disk method problem. But if I were to try to use the disk method, I would need a right minus left situation for my radius. And furthermore, I would need the right function to be a function of y. So if I tried to start this problem, I would extend from what looks like 0 to 1 here. And then I would go from right minus left, but the function I'm given is in terms of x. And so there's no way I can solve this function that has, all of these x's in 3 different terms. There's no way I can get that x by itself to make it into a function of y. So the disk method that it looks like it's clearly set up to be is not an option here. So what I have to do is I have to use shells. And again, I'm told that in the problem, but just to kind of go over when I do and when I don't need the shell method. So in creating shells, I actually want to just draw one out here. So you'll see one of the shells drawn in this right solid image, but the shell method tells me that I'm going to need a height. Well, I just drew a height right now by finding a top minus bottom, and I'm going to need a radius. So I'm going to try to draw one of the shells. I'm going to draw a little cylinder. So it's going to look something like this. And I'm just going to actually over here write out the formula to remind myself. The general formula is 2 pi goes in the front, and then I'm going to extend from x equals a to x equals b. So notice that I have a function of x, and I'm rotating around a vertical line, but everything still stays in terms of x, so I didn't need to switch anything to y's. So my limits of integration are going to be from 0 to 1, but they are the 0 and 1 from along the x-axis, not the 0 and 1 from along the y-axis. So x equals 0 to x equals 1. And then in general, the formula calls for the radius as a function of x and the height as a function of x dx. So the radius, so I want to generalize the radius. I don't want to find the radius at a particular numerical value. I want to find the radius at any x I choose between 0 and 1. So this is the random x I decided on, and so if I wanted to find the radius in general, I'm going to use right minus left to find the radius. So the right function here is just x. So the radius is going to be x minus 0. So that's what I'm going to substitute in right here for r of x. So that was found by doing right minus left, the right function just being x. So I don't want to give it a numerical value. And then the height, well, at this particular x that I've chosen, the height is found by doing top minus bottom. So the top function is this whole thing here, this cubic, and the bottom function is the horizontal line at 0. So it's going to be x times my height is 1 minus 2x plus 3x squared minus 2x cubed, and then dx. So this extends from 0 to 1, and I have to have my 2 pi in front. So this is the formula that is going to find the volume of this three-dimensional object, which kind of looks like a smushed Hershey's Kiss that's happening. So again, I didn't have the option of using the disk method in this particular scenario because there was no way of obtaining right minus left and rewriting this function in terms of y. So that's different than the notion of the right minus left of just this particular radius. So this radius is just a numerical value, and it's found by doing whatever numerical value this is. So this represents some numerical value minus 0. So between 0 and 1, let's say I picked 0.4. So what's the radius of this particular shell? 0.4 minus 0. So that's what the x minus 0 stands for. It's not this blue function written out as a function of y. It's a completely different right minus left situation. So I know that's an issue that tends to confuse people. If I can do a right minus left here, why can't I do a right minus left up here? So it's not the same thing. This right minus left is representing the numerical value of the radius at any x chosen. So just like in the previous examples, we're going to focus on the setup. So this is the setup that would find our volume of revolution using the shell method. Alright, now let's use the shell method to find the volume of the solid obtained by rotating the area under 3x minus x squared about the line x equals negative 1. So we're solving that initial problem that we took a look at the very beginning that we said couldn't be solved by using the washer method. So we're rotating this region here around the vertical line x equals negative 1. So let's just go ahead and draw one of our shells, and that's going to be my best advice in using the shell method is to draw a particular shell. So I'm just going to choose any x value between 0 and 3. So that's the limits of integration that my region extends from 0 to 3. And if I were to draw a shell here, so this is my axis of rotation. So if I were to draw a shell, well, here's the shell's height at this x that I've chosen. And I'm going to have this gap that's happening here. So let me attempt to draw one of my shells, so one of my cylinders. So this is going to be one of my cylinders, and I'm going to have a radius that extends to the axis of rotation here. So my radius, let me attempt to use a different color for the radius here, is going to have to be right minus left, and let's remember that this line here is x equals negative 1. So in general, my volume formula, just to write it out one more time, 2 pi the integral from x equals a to x equals b. So a and b come from the actual region, where the region extends from on the x-axis, so from 0 to 3. And then in general, I'm going to want my r of x, and I'm going to want my h of x. So r of x, the radius at any x, well, I chose any x between 0 and 3, the radius is going to be right minus left. So right being x, so that's what I'm going to substitute in first. So x, and then minus left. So the left function here is going to be negative 1. So x minus 1. So this here represents my radius at any x. And then to represent my height, well, my height was right here, and that's found by doing top minus bottom. So the top function, this is the graph of 3x minus x squared. So 3x minus x squared, and the bottom is right along the x-axis, which is y equals 0. So 3x minus x squared minus 0. So this is the formula, and I'm going to need my dx just to remind myself everything needs to be in terms of x. So even though I'm rotating about a vertical line, in using the shell method, I want everything to be in terms of x. So if we want to just shorten this up, 2 pi, the integral from 0 to 3 of x plus 1, and then times 3x minus x squared dx. And so key differences that we want to notice are there's a 2 pi in front instead of just a pi. The fact that we're rotating around a vertical line and we still have x's in our integrand, and that nothing is squared here. So a lot of students just try to memorize formulas and plug things into formulas. It's really better to just try to remember where the formulas were derived from. So in general, the surface area of a cross section that is a cylinder was 2 pi r, because that was the circumference, times the height. So ultimately, this is the area of the cross section. We're still dealing with cross sections and just using them in unique and modified ways to find volume. So this is my setup to find the volume of the solid using the shell method. Alright, now use the shell method to find the volume of the solid obtained by rotating the area between 9 minus 3x, so it's a linear function, this blue one, and 9 minus x squared, so it's this downward facing pink parabola. So our region extends on the x-axis from 0 to 3. And first, I want to rotate this region about the y-axis. So part A, the first part of this problem, I'm rotating about the y-axis. Alright, so if we're using the shell method here, I'm going to pick some generic x value and draw one of my cylinders. So the height of my cylinder extends from the top to the bottom of the region. So this is going to be my h of x. And if I'm rotating around this line here, I'm going to go from the axis of rotation to that height, that top minus bottom, and that's going to be my radius. So if I were to attempt to draw this cylinder now, it's not quite as long. I should have made it a little longer, like that. So this one should extend a little bit more, and that's going to be one of my cylinders, one of my cross sections. And this distance here is going to be my radius. So my radius is going to be x minus 0. And my height is going to be found by doing top minus bottom. So in this case, f of x is on top and g of x is on the bottom. So let's go ahead and set up our integral for a. We have 2 pi times the integral from x equals 0 to x equals 3. And our radius is right minus left, so x minus 0, which is just x. And our height is top minus bottom of the region, so it's 9 minus x squared minus, and the bottom function is 9 minus 3x. So this is the setup that I would need for the height, including the parentheses, because this negative distributes. Now, if you wanted to simplify it, we could and distribute the negative to make this a little bit shorter. So I'd have 9 minus x squared minus 9, so the 9's would cancel. So I have negative x squared, and this minus become a plus. So I have plus 3x dx. So this is the setup required to find the volume of that solid if I rotate around the y-axis. And now let's see what changes if I instead try to rotate around the line x equals 4. So x equals 4 is a vertical line, and the line happens to be to the right of this particular region. So now let's erase what we have so far, and let's try to draw one of our cylinders. So I'm going to stick with choosing this x. So the x that I choose is still between 0 and 3, where the region extends from on the x-axis. So if I were to try to draw a cylinder now, well, the height is still top minus bottom, still f minus g. And now if I'm rotating around this line here, my radius extends to the axis of rotation. So I'm just going to go ahead and draw one of the cross sections, so one cylinder, or I'm going to try to draw one. So something like this. This is going to be one of my cylinders. And so the only thing that's going to change is the radius. And the radius is still obtained by doing right minus left. But now, what function is on the right? Well, this is my radius here. What's on the right is 4, and what's on the left is x. So my setup for b is 2 pi, the integral from 0 to 3, and these are still x values. So the radius is the only thing that changed. The radius, right minus left, is 4 minus x. And the height is still top minus bottom, which I can still go ahead and use the simplified version because top minus bottom didn't change the functions. So it's still negative x squared plus 3x dx. So I'm obtaining my radius by going from the axis of rotation to that particular x value I chose when I attempted to draw my cross section, and I'm doing right minus left. So these are the two setups needed to find the volume of the solid when I rotated around the y-axis and the line x equals 4. So let's remember the y-axis is the line x equals 0. So if I rotate around a vertical line of the form x equals a, I can use the shell method without turning my functions into functions of y if they are already functions of x, and that provides the benefit for the shell method. There's no need to rewrite these functions in terms of y. Alright, so the shell method is not unique to rotating about vertical lines. We can also use the method of cylindrical shells to rotate about a horizontal line, so a line y equals. And so if we're rotating around a line that is y equals, we're going to need a function in terms of y. And that function will need to be continuous and defined on C to D, where these are y values. Then the object obtained by rotating the region about a horizontal line is the exact same formula, but now everything is in terms of y. So y goes, my integrals go from y equals c to y equals d of the area of the cross section as a function of y, which is still 2 pi r times h, but r and h are now functions of y. So we're still looking for a shell radius and a shell height, but now the tables have turned. To find the radius, we're going to need to do top minus bottom, and to find the height, we're going to need to do right minus left. And again, all of these functions are in terms of y, and the limits of integration are also in terms of y. And again, steps for using the shell method, we're going to draw a shell still, but this time at any y in the interval. And then we're going to sketch the radius from the axis of rotation to y. And this time we're going to write it as a top minus bottom, and this must include the variable y in it. And then we're going to find the height and write that as right minus left, again as functions of y. Alright, so here's one example that we're going to do when we rotate around a horizontal line. So use the shell method to find the volume of the solid obtained by rotating the area between 9 minus x squared and the x-axis about the x-axis. So here's the region we're talking about, 9 minus x squared, and it's bound by the x-axis. And we want to rotate it around the x-axis. So here's the indication we're rotating it around the x-axis. So since we want to use the shell method, we go ahead and choose some value between 0 and 9. So those are the limits of integration. They come from the y-axis. We just choose some y, and we create a cylinder. We create a shell. So this time, our radius is going to extend from y to the x-axis, so we start from the axis of rotation to the value that we've chosen, and then let's go ahead and draw one of our cylinders. So our cylinder is going to look something like this, so now it's going to be a can on its side. And to find the radius, again top minus bottom, and then to find the height of the shell, so since it's lying on its side, its height is right minus left. So let's go ahead and set up our function. We have, or our integral, we have volume equals 2 pi, the integral from y equals 0 to 9, so they need to come from along the y-axis since I'm rotating around a horizontal line. So y equals 0 to y equals 9, and then top minus bottom. So the top is y, and the bottom is 0, so y minus 0. And then I'm going to need to do right minus left. Well, in this particular problem, I was given y as a function of x, but I want x as a function of y. So I'm going to need to rewrite this function in terms of x. So here, if I add the x squared to the other side, I get x squared equals 9. If I subtract the y to the other side, 9 minus y. So then x equals plus or minus radical 9 minus y. And hopefully you can see that written here. I have x equals radical 9 minus y. And it's the positive version because I'm up here in quadrant 1 where x and y values are all positive. So I choose positive radical 9 minus y as the right function. And the left function is x equals 0. So in my shell's height, I'm going to need the square root of 9 minus y minus 0. So the shell method isn't always exempt from having to solve the function that you're given to make it in terms of the other variables. So we had y as a function of x. We needed x as a function of y since I'm rotating around the x-axis, which is y equals 0. And one of the things I hope you thought about at some point is, was this the most efficient method to use? We were told to use the shell method, and we did to get practice on when we're rotating around a horizontal line using the shell method, but hopefully you were thinking, well, I'm rotating this region here around the x-axis, and this region is perfectly up against the x-axis, so the better method to choose would have been the disk method. So if we would have used the disk method, I would have pi, and then times the integral from 0 to 3, so I even have my limits of integration, so x equals 0 to x equals 3. and then the radius squared. Well, my disks would look something like this. So the radius is top minus bottom. So the top function, and this is already in terms of x for us. So we can write 9 minus x squared with no rewriting squared dx, and that was much easier, didn't require any additional work to find the volume of the same exact solid. So we were told to use the shell method, but in general, you won't be told necessarily which method to use. It'll be up to you to determine what's the most efficient method. In certain cases, the shell method will be the only option, but in some cases, you will have the option to decide what's best and what's easiest to use.